I guess just a quick intro to start with. My name's Joel Snape. I currently work for Netitude. I've been doing security for about 10 years now, I suppose, before it called it cybersecurity. And I'm a bit of a security dog's body, so my interest is interesting questions, interesting problems, and so I get dragged into all sorts of things. My notional role is doing marine cybersecurity, but I tend to get caught up in a lot of other things. And just before Christmas, we did a bit of a deep dive into a piece of mail called IcedID, which we did in conjunction with Mimecast. And we have an internal conference once a year called DEFCON, where we sort of talk about the things we've been working on. And I did this talk, or a variant of this talk at that. And the aim really is it's not so much about the specific piece of malware per se, although it's kind of interesting, but it was really just to talk through the process of going from an unknown sample through to actually having a bit of a clue about what it was. We were given it with no context at all, so we had to kind of start from no knowledge. And then I'll touch on just a little bit of fun we had with it at the end, in terms of tweaking it to our advantage in terms of some of the things that we do. So IcedID is I've put a banking Trojan there. It's really a sort of Infostealer. They're interested in getting access to people's machines and stealing as much information as they can about all sorts of things that user might be doing. So it started out with passwords for people's online banking, but it ends up being a lot more than that. And even if they get an interesting infection in say an enterprise, it might move into selling that access to other groups, or potentially sort of leveraging that access to deploy something like ransomware. So it's an interesting bit of malware to be aware of. The group that spreads it is often called TA551 or hack, and it's loosely grouped around the methodology that they use and the types of malware that they use. But I'm not really a TI analyst, but I sort of play at it, and I don't track them too closely. But that's the kind of loose grouping that I operate within, just to set some sort of parameters at the start. So we were asked to take a look at this, and like I said, we started from very little knowledge. And as usual with this kind of stuff, it starts with an email. Though this one was in Japanese. Fortunately, Google Translate exists. So we were able to translate it and get the "Good morning, please check the attached file, zip file decompression password," and that's the password there. So this is kind of one of the really common techniques for spreading malware. You send it out in an email, but it's basically the #1 way this all operates. And being, obedient users will open up that zip file, will put the password in. Obviously, the password's there to try and stop kind of naive security tools from being able to scan the malware. So we put that in, we open up the zip file, and we get a Word document. And again, it's all in Japanese. So one of the things about TA551 is that they like to target quite sort of geographically. So they will kind of have campaigns where they'll be targeting Italy for a bit, and then Japan for a bit, and then they'll do some English language speaking country somewhere, and then they'll go back and do Italy and that kind of stuff. So you see lots of variants of this in different languages. Again, I can't speak Japanese, but Google Translate comes out with that text at the bottom there. And again, if you've done any kind of malware analysis, you'll have seen this. This is super common. This is a Word document, and it's asking you to click the little yellow bar that you get at the top that says enable editing and enable content. And what that means is this is trying to run a macro. So they've put some macros in the Word document, and they're trying to get you as the user that's opened it to run those macros. So I guess our next step is trying to work out what those macros do, because obviously we want to really understand what is happening. And there's kind of two ways really of doing that. You can do it dynamically, by which I mean you can open the document in a sandbox or just on a machine with something like Process Explorer running, and you can kind of watch what it's doing. And that's fine, that's good, that's one approach, and we did that. And you can also do more kind of static analysis. So that means taking the document and putting it to pieces and really trying to understand what it does. And we did that too. So in that last case, that's quite useful because often malware will have guardrails in it that will stop it executing in certain contexts. So in this case, it might only execute if the language of the machine is set to Japanese. And you might not know that up front, obviously you want to guess in this case. And you might not have your sandbox configured in quite the right way, or it might need to run for 15 minutes, or it might need to run on a host that does a particular thing, like opens a program or something like that. So to do the static analysis, the first thing we want to do is get a copy of the macros. So in a Word document, one of the ways you can do that is with a program called OLE dump. There are other programs out there for doing a similar sort of thing. But what this will do is let you take the stream or the macro data, decompress it if it's decompressed, and dump it out as text. And you get something like this, which is, again, pretty typical if you've done any kind of malicious document analysis. You'll see there's a whole bunch of stuff that's meant to make our life hard. So all the variables have really shitty names like this, like AI, WDG, that you have to kind of trace through. You've got lots of like arithmetic operations that may or may not be meaningful. A lot of them are just in there for filler. And you'll have lots of rich comments like the ones at the bottom there, which are just random words that are shoved in there to make your life harder. And again, there's different approaches you can take to this. One tool that I like is something called Viper Monkey. I like it mainly because it's such an awesome idea, and I wish I'd come up with it myself. But this takes the VBA code and attempts to emulate it. Really, is probably the best word to use. So it's not actually executing it, but it's trying to work out what it does and log interesting functions. So you can see at the bottom here the different VBA built-in functions that were called. And from this, we can start to get an idea of what the macros are doing. It's not perfect, and I'll come on to that, but we can see up here, it's got an interesting function call. It's pulled out for us, which is copying, file copy, something called mshta.exe into your local temporary folder. You can see that it's opening a file in your temporary folder called in.html, and you can see that it's trying to execute that. So what this is doing is it's using mshta, which is a built-in Windows component for running HTA files, which are compiled HTML applications, and it's using that to try and execute in.com, in.html, which it has dropped, and you can see here it's dropped a file. Now this is where it's not perfect, and that dropped file hash is actually the hash of an empty file. It's got thousands of hits on VirusStation. None of them are used because it's just 0 bytes long. So we have to try and work out what actually happened there and why Viper Monkey wasn't able to extract that file. Now I have to admit, I think I was on holiday this week, and another guy in my team did the mind-numbingly dull work of reversing all the obfuscation that's in the macro text. But you end up with something like this. You end up with a script that looks something like this, where you are using an XML HTTP object, which is a way of requesting files. You're saving it in. Oh, sorry, I'm getting ahead of myself. What happens there is the in.html file is actually kept within the resources section of the Word document, which is why Viper Monkey can't quite access it. I don't think it's at the time anyway. It didn't quite have the logic built in to do that. So we can extract that in.html file from the resources section of the document and take a look at it. And again, that in.html file is heavily obfuscated, but we can deobfuscate it, and that's the mind-numbingly dull work that my colleague did. And we end up with this. And what this is an XML HTTP stream, which is a way on Windows of downloading files. And you can see we're going to do a GET request to a URL, which we passed as a parameter, which we reverse and then decode. And then we're going to save that as temp.temp, and then we're going to run it with regserver32. So what this means is the macro is going to write an HTA into your temporary folder. It's going to run that HTA, which is going to go off to the internet. It's going to download a file, it's going to save it into your temporary directory, and then it's going to run it with regserver32. So regserver32 is a program that can run DLLs. So that means that we're expecting to retrieve a DLL. And it's going to try and execute that. Now the only bit left is what's that U, because obviously we're kind of interested in getting a copy of this DLL. Now we want to know what it is, what the next stage is. So we need to extract that. But we can see earlier on, and again, this beautifully deobfuscated code that my colleague produced. We can see we've got this here, which is pretty obviously a reversed base64 string, and that matches up with what we saw here, reverse string and decode. So we can use, you can use whatever tool you like for that, but CyberChef, if you've never come across CyberChef, I recommend having a look at it. It lets you do all sorts of kind of encoding, decoding, encryption kind of tasks really, really quickly, and just try things out, see what works. So we can put our input in here. You build what's called a recipe, which is a set of steps. So here we're going to reverse it by character. So I'll flip it around, and then we'll decode it from base64, and then you get this output here. So the malware is going to go off to that URL, and it's going to attempt to retrieve DLL. So excellent. We're in a good position now to look at the next stage of execution. So we go off to that URL and we try and grab hold of it, and that's what we get. It couldn't resolve it. I think at the time it was disputed or frozen. And this is, again, really super common if you try and do any kind of malware analysis. You need to be really on it. And unfortunately, in this case, we were given the sample a little bit late for analysis. So we were a little bit slow to the party here. And the domain had been taken down pretty quickly. It's a little bit hard to tell. We couldn't tell, I think, from the evidence we had, whether it was taken down by the actors or whether it was taken down by the registrars, and both are super common. So actors will often take their infrastructure down, particularly for the first stage, very quickly, because they want to stop this kind of analysis happening. And they know that most people will open the email. Most people who are going to succumb to the lure will open the email pretty quickly, within a couple of hours, maybe 6 hours, and themselves. And so after that, they can take all of that distribution infrastructure down. And then obviously people are looking out for this kind of stuff and reporting it to registrars. So they are also taking this stuff down. So as an analyst, it's a bit of a race against time. Fortunately, in this case, we were able to get hold of the DLL from a public sandbox, I think, off the top of my head. I can't quite recall exactly where we got it from now. But you can often find samples like that from places like VirusTotal. You can find them from sandboxes where other people have uploaded samples, and you might be able to find them from asking around in the community and seeing if there are any other analysts who have managed to get a copy of the sample. And there's various sort of community forums available for doing that if this is something you're interested in looking at. So sorry, just as a reminder of where we've got to, I'll put this diagram up from time to time to go through the talk, because I struggled to keep it all in my head, and it's useful to have it written down. So we started out up here in the top left with an email, and that email contained a zip file with a password. We put the password in, we opened a docx file. That docx file contained a macro, which drops an HTA into your temp folder as in.html, and then it uses mshta to run that, and that HTA goes off to sa9.763.com and extracts a DLL. So excuse me, which it writes to temp.temp in your temporary directory, and then it executes that with reg server 32. So we're going to be running a 32-bit DLL. So we got a copy of that, like I said, and we want to start to take a look at that and understand what it is it's doing. And so this is IDA, and you can use IDA. I think actually I did the analysis for this in Gidra originally, and then switched to IDA for the screenshots to make me look more professional. But Gidra is good too. Gidra is a free decompiler and disassembler that you can get hold of, and you can put something like a DLL in it, and it will start to make sense of it for you. And this is what we get. So this is IDA, but it's effectively the same. And you can see that it looks like garbage again. And there's a lot of the features that we saw in the obfuscated macro that are repeated here. So we don't have comments because it's compiled code, but we have lots of stupid functions. We have lots and lots of if statements that may or may not run. We have lots of arithmetic, and we've got lots of like tiny little loops. And you can't see it in this screenshot, but there are actually something like 20,000 different tiny little functions that are going to operate. So that's pretty clear that we're not looking at something that was written by humans. It was something that was machine generated. And what this is a packer. So the malware authors will have taken their DLL that they want to execute and run it through something called a packer. And what that will do is it will obfuscate it all, bundle it all up, and make it really hard for an analyst to understand what it is that they're looking at. So we want to reverse that. But again, there's different ways of doing that. What worked in this case was that we noticed that when the DLL was executed, it says you provide a function to execute. And when that DLL entry point function was executed, it started a new thread. So we can break on things like thread entry, thread start, thread end, DLL entry as well, or DLL load for when the DLL is loaded in a debugger. So this is x32 debug, I think. And what you can do then is set these kind of breakpoints. And if we switch to here, so this is the debugger that's broken at thread start, and you can see it's about to call a function. You can see that we've got, it's a bit, this doesn't really tell you about, but you can see we've got things like exit process, and some of the other stuff makes a lot more sense if you just look through some of the disassembly that's in the debugger, and if you trace the execution through, it all makes a lot more sense. So this looks like we've now got something that actually looks like the DLL, and you can dump it out from here. There are options in here to dump memory portions, or you can use tools like PECIV. So PECIV is a really great tool that's publicly available, that can scan a process and look for things like DLLs that are different in memory to how they appear on disk, and other kind of signatures that show that they are hooked or replaced. And you see in this case we've got one hooked DLL, so that's a change to ntdll.dll. I'm not quite sure why that shows up. I can't remember now off the top of my head. But you can also see we've got one that's replaced, and that is our temp.temp DLL. So that PECIV has spotted that that's been replaced in memory, because what's happened is the packer has unpacked that DLL into memory and is now executing it. So from the point of view of PECIV, it can see that it started out with one thing and it's ended up as another thing. And then PECIV will save that to disk for you automatically. And we can load that up. That starts to make a lot more sense. We've got like 32 functions down here. It's sort of not very many, quite reasonable. We've got a lot of sensible imports here, especially you can see a load of HTTP connect and open and stuff like that, which looks promising for understanding what this next stage of the malware is going to do, because it's probably going to connect off to the internet at some point. So from running it dynamically, we could see that it did connect off to the internet to try and get yet another stage. So my first kind of goal that I set myself for was trying to understand how that part of it worked. Where did it get its configuration from? And up front in the malware, we see this little loop. So what these are is sort of basic blocks. So you can see we've got something here that's 204 in hex being moved into a size variable. That's something that I've named it. And then we're looping around this. We can see we've got an I, we're incrementing I, and we're jumping if we've not reached our size yet. And I've called it encoded config, which is something I've obviously figured out. But you can kind of see that we've got some values being read from memory here, and then we're doing some sort of arithmetic operations on them, and we're doing that in the loop for a size. So that kind of looks very promising in terms of potentially unpacking some kind of config, because the config is likely to be obfuscated. You know, looking at the strings, there's nothing in there obviously that looks like instructions for what to do next. So we want to kind of understand this this mechanism here to be able to decode the obfuscated config inside the DLL. And it's fairly straightforward. If you sit down with pencil and paper and scratch your head for a bit with a coffee, you'll figure it out, and you end up with something like this. Now this is actually the mechanism to encode it that I presented here. So along the top here, we've got HTTP, so a string, and that's represented in ASCII by these decimal numbers, so 68 for H, 74 for T. What happens is it's XORed with its position in the stream, so XORed 0, 1, 2, 3, which gives you 68, 75, 76, 73. And then that is split into two nibbles, so the low nibble and the high nibble. The low nibble is then shifted left by 4, so you end up with 6 and 8. So 6, 8 goes to 6 and 8, and then that's ORed with a 4-bit random value. So you end up with like 62A, but obviously that 2 or that A could be anything. It's quite a nice little obfuscation scheme, because every time you run it, you'll get a different result. So you'll get, so it's better than just XORing it with a fixed key or something like that, because the lower half of each value there is random, so it'll look a bit different each time. So that's quite nice. So we can decode the bit of the blob of memory there, and you end up with something like this. So there's a few sort of flags at the beginning there for various things, but what you'll see is a bunch of domain names, so intel.com, twitter.com, etc. There one argentinacapucho.cu that stands out as kind of probably not being quite so legitimate, and we kind of want to work out what it's doing with those domains. Obviously it's going to connect to them, I suppose, but we can see that what happens when once it's received the page, so it goes off to the domain, requests the page, it loops through it looking for these two strings, so source equals or URL equals, and these are both ways of specifying URLs or parts of a URL in HTML. So you might have image source equals blah, and then this one is CSS, so URL, and then that will give you the path for a file to include. That this one's typically used in like a background image specify CSS specifier, and then if either of those match, I think, oh no, sorry, it'll check those, and then it'll check whether they're in the page, and if they are, it will extract the URL out of there. I've sort of snipped this a bit too close, you can't quite see all of it, and do something with the URL that it extracts from that parameter. And if we look at the argentinacapucho.cu page, we can actually see there background.png. So what's going to happen is it's going to go off to argentinacapucho.cu, it's going to receive this page, and it'll extract background.png from there, and it'll go off and retrieve it. Now, that could obviously be anything, but I've only ever seen them, or certainly when I did this, I'd only ever seen them use background.png. So they're not taking sort of full advantage of all the features of their malware there. And then the other thing is, obviously, if they go to facebook.com, it will also probably have something like this, or an image source or something like that. So the malware will generate a fair bit of kind of legitimate traffic as well, to kind of help it blend in on the network. Now, there's one other flag that's set in the config, which means that if it's the actual C2 address, it sends off a load of cookies, and they're kind of things like config version. There's an encryption key, which we'll come back to later, that's set by the malware. Windows version information. The one that's kind of really interesting is the processor, what I've called processor information there. So that contains a bit of information about, like, you know, it's an Intel 4-core, whatever. But it also contains this little bit of data that comes from a timing loop. So what they do is they generate a value by calling an instruction called RDTSC. So RDTSC is an x86 instruction that gives you effectively the number of cycles since the process was last reset, I think, off the top of my head. So, that's probably not quite its formal definition, but you can think of it that way. So that's effectively a timer. So they save the time there. They call an instruction called CPU ID, which gives you information about the processor. So you get various bits of information out of it, like the number of cores and who made it, all that kind of stuff. There's all sorts of flags and things like that. And then they call RDTSC again, and you can see they sort of subtract the two times. So they're basically recording how long it takes to run that CPU ID instruction. And then they do it again down here, but without the CPU ID instruction. So how long does it take just to run two back-to-back instructions? And they do that like 32 times, I think. I can't. Yeah, I haven't got where X is set in there, but I think it's 32 times. And they add up all of the differences and then divide them to form a ratio between the amount of time it takes to call the CPU ID instruction versus the amount of time just to call two move instructions. And the reason for doing this is kind of interesting, because if you're running this in a hypervisor, then what would normally happen is that the instructions are handled by the underlying processor directly because of the virtualization extensions that exist in x86. So there's not really a noticeable time difference between a hypervisor and a non-hypervisor running, say, like a move instruction, moving data between two registers. But obviously, when you set up your VM, you can choose like the number of processors. You can say to a degree what kind of type it is, how many cores, how many processors, and how many cores per processor, that kind of stuff. So the CPU ID instruction actually, I think, causes a fault and then has to be handled by the hypervisor application itself. So obviously, if you're running this on a hypervisor, that instruction is going to take a lot longer to return in relative terms than it would if it was running on a physical machine. And so by recording how long that takes and how long it takes without those structures, sort of generating the difference, you can the ratio. So you can figure out how likely you're running on a hypervisor. So I thought that was quite a neat little trick. I'm sure it's reasonably common, but I thought I'd just run through that. So they package that up with all of those other cookies, and they go off to argentina.capucho.ce, and they download background.png, which looks something like this. Now, again, life is never actually that simple, and we struggled for a bit to get a copy of background.png from the same version of malware that we had, but we did eventually manage it, and it's worth looking at what it's doing. So it's downloading a PNG file. This is what you get if you're just a normal user. But if you meet all of their conditions with all of your cookies, you have to jump through all of those hoops, like the timing things and the location and what IP address you come from, all that kind of thing. You get still a PNG file, but a bit of a special PNG file. So their DLL will load this PNG file, and it will start looping through it at various offsets. And I'm not going to go into the PNG file specification, I don't think I have time, but it will be looking for this thing called IDAT. So IDAT is a section identifier within the PNG file. It stands kind of for image data, and normally you'd expect that to be followed by the compressed image data. However, in the case of this malware, they've used the PNG kind of like file format, but instead of image data, they have their next stage of the malware. So they'll loop through looking for the IDAT section, then they'll extract some values from it. So here in the sort of like dark blue here in the middle, you've got IDAT, and you can see the ACI over on the right side here. Immediately before that, you've got a length, which is how the PNG format works. So you can see you've got these different sort of headers. You've got PNG, I header, sRGB, gamma, fizz. So IDAT here with its length immediately before that. Here in the sort of like light blue, you've got a checksum that they use to validate the contents of what they extract. And then in red here, you've got a key length. And there's two options here. So the contents of the file will be encrypted. They'll be encrypted either with the encryption key that the malware provided in the cookie, and I mentioned that a little while ago, or it'll be encrypted with a fixed key, in which case this will be a key length like 8, and then the next 8 bytes will be the key. And that's quite cool because they can encrypt each file randomly, well, with the key that the malware provides, which is generated randomly. So every time you connect, you get a different file back. So that evades any kind of like naive attempts to do hash matching or anything like that, because obviously the hash will be different every time that anyone gets one of these files. And again, so this is the PE format. So once you extract it, it has a custom header within it, which contains things like a shellcode length, which gives you the length of this section here, header length, which gives you the length of this gray section, and some other information that's used later on. And it's quite nice. So they've got a bunch of shellcode, which is just run directly, and they have a kind of custom PE format, which they've developed, which has its own kind of header. It's different to a PE header, but you can kind of figure it out if you look at it hard enough. And then at the bottom here, it has a file that's attached. And this is the stage 2. And this will either be a DLL or executable. And then depending on a flag in the header here, the DLL/exe flag, it will be dropped to the DLL file name or .dll if that's DLL, or .exe if it's an exe. And then it'll be run either directly if it's an executable, or using reg service 32 again if it's a DLL. So they've gone to all this trouble right there in shellcode, a custom PE loader, custom PE with a custom PE header, their own import table up here. And then all that custom PE does is disable Windows Defender, which I found really disappointing. I'm spending quite a lot of time reversing that and trying to work out what it did. And then all it uses like 3 different, I think it uses like the registry and the WMI and something like that to disable Windows Defender. So that's quite dull, really. And then it executes stage 2. But this is obviously something they've developed. It's like a library, and they do use it later on as well. But it's a bit random why they've gone to all this trouble for this stage here. So just to remind us where we are quickly, I've got this diagram back. So we've dropped our HTA. That's dropped DLL, which is the DLL that we've been looking at just now, that we unpacked and we've been reversing. That goes off and downloads background.png. That PNG file gets decrypted and saved into your temporary folder as another DLL, something .dat. was that reader wheel.dat, I think was the convention that was used in this version. Although it's kind of like the semantics where things get saved, what names they have changes quite regularly. So we want to take a look at that DLL and work out what that's doing. And I'm not going to go into that in detail because it is broadly the same, which is again a bit weird. This is kind of like an earlier version of the malware in some ways. It's packed in the same way. So we'll unpack it and we can start to take a look at it. It goes off and connects to a URL that's /image/ID, and then these values here, these sort of printf placeholders, of things like the encryption key and Windows information, that kind of stuff, which is what the earlier versions of the malware used to do in its first stage. So they've sort of mixed things up a little bit again to try and evade detection. It has a config section, which again is which is encrypted in this DLL. It's encrypted using the same code that the PNG file was encrypted with before. So reversing that once was quite useful because you could just apply it again. I think it was RC4 encrypted. So we can decrypt that just with a fixed key. So we can decrypt that and we can get, now we've got these two domains. So we're going to go off to aspectcores.club and we're going to go to realize oil.cu, and it's going to download yet another PNG file. So just that diagram again. So we're now looking at this DLL here, which we've reversed, and it's fundamentally very similar to the first DLL, which goes off and downloads yet another PNG file for a slightly different location. And then that PNG file is written to app data for persistence. And there's a scheduled task that uses this DLL to load the PNG, because it can also load it from disk and run it. And I think that happens if you log in. It tries to run itself again. And then it's injected into MSI exec. So the PNG file this time around looks a little bit different. The shellcode has got the same sort of custom header. The shellcode, which is run, is a little bit more sophisticated. In this case, it launches MSI exec. And then there's a 32-bit and a 64-bit kind of section that's run depending on the processor architecture, which will inject the payload, which is the red box at the bottom here, into MSI exec and run it in a new thread. So the process for doing this looks a little bit like this. So create process creates a suspended process, MSI exec as a suspended process. There's a switch depending on whether it's 64 or 32-bit, because it needs to switch to the same architecture as MSI exec will be, and it uses Heaven's Gate to do that architecture flip, which is super common. It does virtual alloc write, which will allocate some memory. It will write into that memory the payload. It will set the protections on that memory to be what it's expecting. So some of it will be executable, some of it will be read write, some of it will be read only. It will then create a thread in the MSI exec process, and it will resume the thread, and then the process cleans up and exits. And at this point, you've got IcedID running inside of MSI exec. So the shellcode that was injected to MSI exec will end up with this headless P running inside the process. And if we look at the memory allocations of MSI exec, you can see this bit of memory up here. So this is what we allocated with virtual alloc, and you can see how it's marked. Some of it is read write, some of it is read and execute. So that's obviously like this sort of text section of the PE that contains the code, and then you've got the read write section down here, which would have your variables in it. This section here, sorry, 18 lots of zeros, would actually normally be where your header is, but they blank that out. So you end up with IcedID running inside of MSI exec. And now this talk is kind of like being focused on that kind of like unpacking stage rather than the IcedID malware itself. It is possible to reconstruct that header. We to do that, it was a complete pain in the arse. Yeah, I learned quite a lot about PE headers in doing that. It was quite fun. And you can kind of reconstruct a working executable that you can load normally then into your normal kind of like analysis tool, and start to make sense of what it's doing. It's quite kind of standard functionality, really. There's nothing too exotic about the main core. There's some really good write-ups. I think there's one on Malwarebytes that's still largely true. I think it's a little bit old now, but I don't think they've changed the core of the application much. You can do things like man-in-the-middle proxying, web traffic, browser hooking, browser passwords, credential theft, and it can load additional code modules using that PNG loading mechanism that I talked about. Now, one thing I was just going to try and quickly show you, if I've got 3 minutes, 3 minutes should be okay, is actually running this, and hopefully this shows up okay. It isn't too blurry, but this is kind of like an analysis VM. What we've got here is we've got command prompt here. I'm going to run the first stage. It is the DLL, and I'm going to use it with run DLL32. It's a slightly different flavor to what we were looking at, but that should be okay. Down here, you've got my local temp folder. On the left here, we've got process monitor. So this will show you everything that happens on my system. And on the right hand side here, you've just got this is just DNS logs, so we can see what domain's being queried. There should so I'm filtering this just on the thing that I'm running, so there's too much noise. So you'll see that I'll execute that. It starts off doing its thing, and you'll start to see that we're making some connections down here, and you'll see on the right hand side here we've resolved tumblr.com, instagram.com, and it'll go through. So this is that first config that I talked about, where it's got a load of legitimate domains, so it's connecting off to those. These inadro.arpa ones are just the reverse DNS lookups that are being done by process monitor. So there's a connection to twitter.com, and in a second we should see a connection to one of the actual malicious CTs. There it goes, aerocrass.cu. So that's one of the malicious domains, and that will serve up the PNG, and you can see down here there it's being written to 005 EB blah blah.png, and you can see it's dropped into my temp folder onto the right hand side. So that's the first stage, and that will be now unpacked. It takes a little while. It's there's some sleeps in there just to annoy people that are making videos for demos. In a second we should see that then gets the DLL should get extracted out of that PNG file. So just give that a second. You'll see it suddenly just shoot a load of stuff in. These are some of the connections timing out, I think, to Facebook, because I don't think I allowed it off my VM. There we go. So it's starting to do a few more bits now. I should probably snip this out, no, really, in retrospect. There we go. So it's starting to load a few more DLLs now. So this is the next stage running, and you can see it's dropped this reader wheel.dat file, which for some reason isn't showing up on the right side there. But oh, yeah, sorry, it drops it into the app data local rather than app data temp, so that's why it's not showing up on the right side there. And you can see in the DNS logs here, we're making our requests off to aspect cause club and polite matrix.top, which is the next stage, and that is now getting yet another DLL. Now this is where sorry, let's go back a sec. So this is where I decided to have a little bit of fun, because I had spent quite a lot of time poking at this, a couple of weeks or something. So I wanted to make sure I had a really good understanding of how it all worked. So I decided it would be quite a nice demo to take the guts of the malware and replace what it was doing. You'll have noticed my OPSEC here is particularly lax. That's my favorite username, JD Snape. You'll just see a load of, like, my domain is snode.p, it's my personal domain. So if you're wondering about my lax OPSEC, the reason for that is because I thought it would be fun to take the loaders that we've seen so far and sort of strip the guts out and replace them with my own. So if I just let that go on, what we've got here is, this is my C27, so it's a bit tricky to read. The video encoding's messed up the font a bit. But here you can see the request for aerocrass.cu. And I've had, this is my C2 that I've written in Python. So I've got a request for a first stage image. I can see who the request is from. Look, there's my username and my desktop and a load of stuff. It's x64 blah. There's my key that's in my cookie. So I've got the key. I encrypt my second stage DLL and I send that. And so that is what would have been written to disk as readerwheel.dat. And then that's executed, and I've given it a custom config, which means that it now connects off to aspectcause.club, which again is just pointing at the same C2 server for ease. And I get the key out again and I encrypt the third stage, which means I can put in whatever I like as my third stage. And in Netitude, we do a lot of red teaming, and one of the red teaming tools we use something called POSH-C2, which is open source, and you can go off and grab that off GitHub and play with it. So I thought it'd be quite fun to put a POSH-C2 loader in the final stage. So what we'll see here, this is POSH-C2. So if you've not used it before, on the left-hand side, this is the server part here that's running, and you can see that my implant has connected here. So I've had a new implant connected on this box. And on the right hand side here is the command interface, so I can run commands against that implant. So I'm going to run ipconfig, and we'll see that it's returning down there. And I've kind of cropped it off the screen, which is very helpful. But what I've done there is I've taken the malware loading scheme. So this I'll have to flip back a bit. Sorry, I've lost the diagram. But this whole chain of events here, and I've dropped the right bits in the right places to be able to load my own C2 framework rather than using their malware. So anyway, that was just a little bit of fun we did just before Christmas, just to see how far we could go. So I hope that's kind of been interesting, just a random journey into a random bit of malware. But hopefully it's kind of shown you that kind of like process of going from an initial sample all the way through to having a bit of a clue about what it's doing, and then potentially being able to play with it and use it for your own ends as well, if that's something that you kind of wanted to do. If you've got any questions, you can we can do them now. I've also put my contact details on the slide there, so if you're watching this later on, feel free to get in touch, email or Twitter, whatever suits you best, and I'll be happy to answer any questions that anyone has.